Hello. Today we are going to go over the rest of Chapter 14's practice problems. So start with our Arrhenius equation, and then in separate videos we'll look at integrated rate law and elementary rate laws. Okay, so here we're looking at some Arrhenius equation problems. I'll go through them, explain them, and if you guys have any questions, please let me know. So we have the following reaction: 2N2O5 goes to 4NO2 plus O2 with the following rate constants. So at 45 degrees Celsius we have a rate constant of 4.8 times 10 to the negative 4, and at 60 degrees Celsius we have a rate constant of 2.8 times 10 to the negative 3. We want to calculate our activation energy from this, so we are using the 2-point form of our Arrhenius equation. So we have ln K2 over K1 is equal to negative EA over R, 1 over T2 minus 1 over T1. Again, it doesn't matter what we use as K1 or K2, as long as we use the same temperatures for T1 and T2. Here we're solving for EA, and our R value that we want to use, the gas constant we want to use in this case, is R is equal to 8.314 joules over mole Kelvin, because we are dealing with energy. Our temperatures also need to be in Kelvin, so we add 273.15 or 273.2 in this case for correct sig figs, and we get 318.2 Kelvin for the first one, and 333.2 Kelvin for the second one. Those values can then go in and we could just plug and chug. So we have ln, I'll use, this is 2 and 1, so 44.8 times 10 to the negative 4 divided by 2.8 times 10 to the negative 3. Again, it doesn't matter which one you use as long as you stay consistent. Equals negative EA divided by 8.314 joules mole Kelvin, and then 1 divided by 318.2 Kelvin minus 1 divided by 333.2 Kelvin. We solve for this. We get negative 1.76 on the left side equals negative EA times by 1.70 times 10 to the negative 5. Divide both sides by that. And we get an EA equal to 103 kilojoules per mole. Okay. All I did here, in case you're wondering, I did that and then I divided the whole thing by 8.314 to get this value right here. And then I divided both sides by negative 1.70 times 10 to the negative 5 to get a positive EA, as there was negatives on both sides. Okay. Number 2, changing the temperature of a reaction from 273 to 300 causes the rate constant to increase by a factor of 7. We want to calculate the EA for this. So we've got T1 being 273 Kelvin, T2 being 300 Kelvin. Our K1, we're going to call that X. Our K2, we're going to call that 7X, because it is 7 times the K value. And then we're going to put all of this into our 2-point Arrhenius equation. So ln 7x divided by x is equal to negative EA divided by our R, 8.314 joules over mole Kelvin, times by 1 over 300 Kelvin minus 1 over 273 Kelvin. Okay? So basically, in this case, our x's are going to cancel out, like so. So we're just going to do the ln of 7. Which gives us a value of 1.95 being equal to negative EA. And then I'm going to do all my math. I'm going to do the math within my parentheses and then divide by 8.314. Negative value of negative 3.97 times 10 to the negative 5. Divide both sides by that value, canceling out my negative. And I get an EA equal to 49.2 kilojoules per mole. Okay. I'm just converting in my head. The values I'm getting are for joules per mole, and then I'm converting them into kilojoules just because it is a little less messy. Okay, the uncoiling of DNA is a first-order process with an activation energy of 420 kilojoules per mole. The half-life, or half-time, is about 2 minutes. What is the half-time at normal body temperature? So this is a little bit more complicated of a process. Or it seems like a more complicated process. Let's see. Now, it's a first order process, and it gives us a half-life. We can use that information to figure out our K value. So remember that T1 half is equal to 0.693 over K for a first order process. So our T1 half is 120 seconds. And from this information, we can solve for our K value. Putting that in, we get a K value of 5.78 times 10 to the negative 3 seconds to the minus 1. Okay, so we would say that our K1 is equal to 5.78 times 10 to the negative 3 seconds to the minus 1. And that has a T equal to 50 degrees C, which is 323 Kelvin. K2 is what I'm solving for, but it has a T2 of 37 degrees Celsius, which will give me 310 Kelvin. So I'm going to put all that information into my equation. I also have an EA of 420 kilojoules per mole, which is the same as 4.20 times 10 to the 5 joules per mole. Okay, let's put all this into our equation. ln K2 divided by 5.78 times 10 to the negative 3 s minus 1 is equal to negative 4.20 times 10 to the 5 joules per mole divided by 8.314 joules per mole Kelvin times by 1 divided by T2, 310 Kelvin, minus 1 divided by 323 Kelvin. Okay, so I'm going to solve for everything on the right side. So I'll get ln K2 divided by 5.78 times 10 to the negative 3. Get a value of 6.56 on the right side. I'm going to take e to both sides. And I get a value of K2 divided by 5.78 times 10 to the negative 3 is equal to 705.4. Multiply by both sides by 5.7 times 10 to the negative 3. Oh, excuse me. This is negative 6.56. I was wondering what I did wrong. Let me redo this real quick. Okay, I get that equal to 1.42 times 10 to the negative 3, and then multiply both sides by 5.7 times 10 to the negative 3, and I get a value of K2 of 8.07 times 10 to the negative 6 seconds to the minus 1. Which makes sense. We would expect that value to go down as the temperature goes down. Okay, last question. The decomposition of NaCl sorry, has a K equal to 9.3 times 10 to the negative 5, molarity negative 1, seconds to negative 1, so we already know this is a second order process. At 100 degrees Celsius and a K equal to 1.0 times 10 to the negative 3, molarity negative 1, second negative 1 at 130 degrees Celsius. We want to know what the activation energy for this reaction is. So we're going to put all of these values into our equation. So we have, we'll take this as K1, K2, T1, which is 373 Kelvin, T2 at 403 Kelvin. Okay, let's put all these values in. 1.0 times 10 to the negative 3 for our K2 divided by K1, 9.3 times 10 to the negative 5 equal to our negative EA divided by R, 8.314 joules over mole Kelvin times by 1 over T2, 403 Kelvin, minus 1 over T1, 373 Kelvin. I'm going to solve for my left side, solve for my right side. My right side, I get 2.38, and then on my left side, I get negative 2.40 times 10 to the negative 5. Divide both sides by 2.40 times 10 to the negative 5. And I get it AA equal to 99.1 kilojoules per mole. I now want to know what the value of K is at 200 degrees Celsius. So now that I have my EA, I could use either activation energy with their temperature and then put it in for there to solve for K at 200 degrees Celsius, which is a temperature of 473 Kelvin. So we're going to solve for K2. We'll call this T2, and I'm just going to use my initial T1 and K1. I need to put this back into joules per mole. My EA. Okay. Solve for everything on the right side. We get ln K2 divided by 9.3 times 10 to the negative 5 equal to 6.76. Take e to both sides. You get 862. And then multiply both sides by 9.3 times 10 to the negative 5. We get a K2 value equal to 8.02 times 10 to the negative 2, molarity negative 1, seconds negative 1. Voila! That is all.